Hi everyone, this video tutorial is for my Year 10s to help you with your upcoming exam for Semester 1, and it's all about motion graphing. Now this is one of two parts of this video, and we're only going to focus on distance time graphs for the time being. Now the two types of graphs that you've learnt about this semester are the distance time graph and the velocity time graph. It's really important to know the difference between these two because it's really easy to get caught out and to calculate the wrong property if you're not really sure what graph you're looking at. So the ones we're going to be looking at this time, distance time graph, pretty obvious if you're looking correctly that this one has on the y-axis, it has distance, and on the x-axis you have time. Whereas for the velocity time graph, the big difference is that you've got velocity on the y-axis. Now, the couple of key terms you really need to know, and if these aren't in your glossary or somewhere on a post-it note or somewhere in your workbook, they really should be. Because if you don't know what you're talking about, it's really hard to understand this video. So the key words here are distance, which is pretty much a measure of how much ground the object covers as it moves. So we usually measure this with our standard units of kilometers, meters, centimeters. Probably meters is going to be your standard one, with kilometers showing up now and again. Now, time is the duration specifically of the motion of the object. So when you're talking about time, it's about the particular time that the object's moving. So it can be in seconds, minutes, or hours. And our speed is the change in distance over time. For other parts of your course, you'll be needing to calculate this in numbers, but for the motion graphing, you're mostly looking at the patterns that you see in the graph itself. So for speed, you could have something like a person walking 800 meters in a 20-minute period. To calculate their speed, you would take the distance covered, which is 800 meters, and divide it by the time it took to cover that distance, which in this case is 20 minutes. Now the important thing here is watch your units. For the units for speed, use the units that you use to do the calculation. So if your distance is in meters and your time is in minutes, then your speed is going to be in meters per minute. In this case, it happens to be 40 meters per minute. Now, distance time graphs are here to illustrate visually how an object is traveling and the distance it's traveled by that object over a particular given time. Now, sometimes these objects may be staying still, they may travel a distance then stay still, or they may travel a certain distance using a given speed. Now, this average speed can be calculated on this graph directly by calculating the gradient. For those of you who aren't quite maths minded, the gradient is basically the slope of a line that is on a slight angle, and the gradient for this particular section of time is your change in distance over the change in time. So for this example, we're just going to show you how to do the speed between these 2 points, point A and point B. So point B is here. Now these ones are actually quite easy. If you start from the very start of the graph where it's at 0, 0, everything is a lot easier. You don't have to do too much complicated mathematics. So if you want the speed, which we're going to represent with an S, it is basically the change in the distance over the change in time. So the first thing to do is find out how our object is actually changing its distance and its time. So if you look between point A and point B, the distance at point B, if you look across at our graph to this point here, it actually used to be 0 kilometers and now it's gone to 3 kilometers. So the total distance that it's covered in this first period of time is 3 kilometers minus the 0 kilometers that it started at, so the distance covered is 3 kilometers. As I said, if you're starting at 0, 0, it's very, very easy, but I'm going to show you the ways to do these despite anywhere you might start on the graph. It doesn't have to be at 0, 0. Now the same way, the time traveled. Now the time that it took to get to point B, you'll read off the x-axis, and at point B, the time it took to get there is 5 hours. And it started at 0, 0, which means that it started off at a 0-hour time period. So the total time it took to get from A to B is 5 hours. Now going back to our original formula, our speed is going to be the change in distance over time. Between A and B, the object changed 3 kilometers, so it traveled a 3-kilometer distance in a 5-hour time period. Now if we put that into our trusty calculator, you'll find out that that is equal to 0.6. Now our unit, as I said before, use the units that you put into the formula in order to get you the correct unit for the speed. So here we've got 0.6 kilometers as our distance per hour, which is our time. So between point A and point B, the speed of this particular object is 0.6 kilometers per hour. Now, a couple of other things to look out for in these graphs. Not everything is based on a gradient. There are certain points in the graphs where the graph shows a very flat line. Now this indicates that there is no change in distance. So for instance, if you look at between point B and C, that over the duration of this motion, or lack of thereof, between the time of 5 hours and 8 hours, the object remains constant at this 3 kilometre mark, which means that the object is not moving. It has moved 3 kilometers away from the position it started at, and then for that duration of time, it stays exactly where it is. So anytime you see a flat line, such as between B and C, or between D and E, it means the object is not moving in whatever position it happens to be at the time. Now, special case, if it happens to be lying flat along, you can't really see that very well, but if it lies flat along the x-axis, it means that it's still at its starting point and it still hasn't moved. So if you're at home and you're trying to get ready for school and you haven't quite left the house yet, you'd be at that point. So when we're looking at this graph, there's going to be possibly several sections where you're going to see a gradient. So in this case, we see one between A and B, C and D, and E and F. Now, if you're looking for the fastest time, you need to find the highest gradient or the steepest gradient. And sometimes you can tell this just by looking at the graph. But be aware that sometimes this particular speed that is going to be the fastest isn't always going to be positive. So if we look at between A and B, it is a positive speed. Between C and D, it is a positive speed because you go from a lower point to a higher point. Between E and F, it is a negative gradient, which means that the object is moving back towards its starting position. So if you think about this distance of being x equals 0, that basically means home, where the object started at the beginning of the graph. So if you see that the object is moving upwards, it means it's moving in a direction away from the position it started at. Whereas if it's moving down y-axis, it means it's returning back to the position it started at. So that's the only thing that positive and negative mean here. So if we're looking for the fastest speed, it doesn't necessarily have to be a positive speed where the slope is going upwards. It may in fact be a negative speed which is going downwards. Now, don't confuse this negative speed with negative acceleration. It is not slowing down or speeding up just because it's going negative. All it has got to do with is the distance away from where it started at. If it's moving upwards on the graph, it's moving away from its starting point, and if it's moving back down, it's returning back to its starting point. So be aware, you're probably going to be asked a question where you're looking for the fastest speed. Be aware that sometimes the slope may be negative, going downwards, it still is probably going to be faster. I'm going to go through an example problem here. This is actually off one of our work booklets. I'm going to walk you step by step through it, and if you can do all three of these standard type of problems, you shouldn't have any issue with doing what's on the exam. Now in this example, Margaret has been on a bike ride, and the graph here on the right is showing her distance that she travels from home on her bike. Now our first problem is going to be calculating Margaret's average speed over the first hour. So if we look at this graph, you could see that here we've got our time in minutes, so our first hour is the 60-minute mark. So if we read up this graph, you could see that this point here is the point after the first hour. And we can see the distance at this point is 12 kilometers, and our time is equal to 60 minutes. Now I recommend always staying with the units that the graph is using, even if it refers to hours or something similar in the question. Stick to the units that are in the graph, it'll make your life a lot easier. So if we're looking to calculate the average speed, the formula for our speed is the change in distance over the change in time, or the gradient of the graph. Some of you who use gradients, if you do rise over run or y2 minus y1 over x2 minus x1, feel free to use any of those. They will all work for you. Now here, the change in distance, she starts off at 0, 0, which makes it handy for us, and then she ends up 12 kilometers from home. So the total distance that she changes between the time she started and the first hour is that 12 kilometers minus the 0 kilometers she started at, which gives us a total distance of 12 kilometers traveled. Now her time, she also starts off at a time equal to 0 because she hasn't moved anywhere yet. And it took her 1 hour or 60 minutes to travel this particular distance. So the time taken is her 60 minutes minus the 0 minutes that she started with, as this is a starting point, which means her time is equal to 60 minutes. Now if we go back to our formula, the speed that Margaret was traveling over this particular time is equal to the distance over the time, which is equal to our 12 kilometers that she traveled over the 60 minutes it took her to do it. And that's going to give us an answer of 0.2. And we're also going to use the units that we put into this formula, which means she has 0.2 kilometers over minutes, not over hours. If you want to do over hour, you're going to have to change the number that you put in here. But since you put in 60 minutes here, you're going to give an answer that is kilometers per minute. Now for the next part, during which time did Margaret rest during her ride? Now, as we referred to earlier, anytime you've got a steady gradient going up or going down, the object's in motion and it's going at a steady speed. The time where she's not going at a steady speed is where the graph is flat. And that means that she has stopped and is stationary at the particular point which she happens to be. In this case, she travels 12 kilometers away from home and it took her 60 minutes to do it. And then between the time of 60 minutes and 80 minutes, I think that's not quite drawn. Yep, that's drawn quite right. The grade is flat, and that means that wherever she happens to be, she is no longer moving. So the time where Margaret rested was between the 60-minute mark to the 80-minute mark. After that point, because this gradient is a downward gradient, it means she turned her bike around and she's heading back towards home. So the third part of our question is to measure Margaret's average speed on her return trip home. Now we don't have a time period given for this question, but as I said before, home is where y equals 0. So for her to return home, we're going to talk about this particular point here and then the gradient she took as she rides her bike directly home. Our formula that we're going to use here is we're going to still find the gradient of that particular part of the graph. It'll just be a little bit more tricky because we're not starting at a point where she has a 0, 0 starting point, so 0 time and 0 distance, but it's still not particularly hard to do if we follow the same formula. Now, the distance she traveled, so her change in her distance, she ends up at home, which means that she ends up traveling back to her 0 point. So she ends up traveling 0 kilometers minus the point she started at. Now here, the point she started at was 12 kilometers from home, which means that she traveled a total distance of 12 kilometers. You can leave the negative there. The only thing that with the negative means that she's traveling towards home rather than away from home. That is a very fine thing here. It's probably more relevant if you're talking about a displacement time graph, but I would put it in there just to make sure that you're doing these things 100% accurately. Now, her change in time. Now, the time she took to do this, she ended up having a total travel time of 120 minutes, which is the time she has when she finally arrives home, but she started at a certain point. If you read off the graph, she started 80 minutes after she started her travel. So because she finishes this particular part of her travel at the 120-minute mark and she starts it at the 80-minute mark, the time over this particular period is 40 minutes. Now be aware, when we talk about the change in time, we're only talking about the change in time in the specific section of the graph we're talking about. You're not talking about the entire length of time she spent on her bike. This is talking about her return trip home, which is from this upper point here back to her return point. So the time taken for her to do that is a 40-minute time period. Now back to our formula, our speed is going to be the change in distance over the change in time for her return trip. In her return trip, she travelled 12 kilometres to get back home, and she took a total time of 40 minutes to do it. I'm going to put the negative here just to be complete. Now if we punch that into our calculators, we end up with a speed of 0.3 kilometres per minute. Remembering as well, we use the units that we put into our formula in order to get the units for the speed. Okay, that's pretty much everything. That is probably the trickiest part of the whole type of these sort of questions. If you can do these, then you're going to be okay. Feel free to email me with any questions, leave comments in the comments section, and I'll see you all at your exams.